You know, you can theoretically, you can, from data here, when you fire this thing, it goes up here, by measuring the change in height of the center of mass, you can back out or determine the initial velocity, right? And then you can compare it to a more direct measurement where you fire it, when you fire it in a, you measure the horizontal range and know the height. It's more direct. So Jeff asked, well, if you know the spring constant and you know the initial and final distance lengths of the spring, you should be able, that gives you a third way of doing it, right? And I don't know if you remember, but I sort of fumbled around with this idea of the shaft here. This part of the shaft hits the stop here, right? And it makes a lot of noise. The noise you're hearing here is, you hear that this is the shaft is hitting the stop. That's a perfectly inelastic collision, right? The shaft comes up against there. What happens in a perfectly inelastic collision? You dissipate energy. So where does that energy come from? That energy has to come from somewhere. Ultimately, it has to come from the spring. So if you calculate the initial velocity here, okay, assuming that all the energy in the spring is going into this, you're going to get too high of an initial velocity because you're losing some energy to the perfectly inelastic collision. And I suspect that's not a small error, okay? It would be interesting to do it in an experiment. It would be really interesting to do, I think. Okay, I just wanted to correct that. Anybody have any questions or comments about that? So then, you know, you can make that part of the lab and you can ask the students, you know, why is your value? I think the value you're going to get here for the initial velocity is, you know, probably going to be very significantly or substantially bigger than the actual value. Then you can ask why, right? You can also ask the instructor, okay, because I screwed up. I missed it at first. Okay, any questions or comments on that? Okay, so we have a problem set today. Begins with a couple of center of mass problems. The first one is number 4. So this is, we've got this upside down square U here, right angle. By square I mean right angle. The lengths are the same, yeah, so it is part of a square. Now they're not, the rods aren't equally massive, but it is symmetric. The mass of this rod equals the mass of this rod, but this rod is different. We're not, we're told, in this problem we're told the masses and this length L here, which is the same for each of the rods. So we'll set a coordinate system here. I don't know, they give you you can put the coordinate system, you know, anywhere you want. You want to choose it conveniently. They've given it to us in this problem, right? So this is going to be the origin. And now the question is, where's the center of mass? Well, the first thing you want to notice here is if I want to balance this in a gravitational field, so you're going to have to do that, you're going to have to imagine we have some massless rods here. Let's say we have a massless rod over here and with a fulcrum right there, okay? We have to look at this physically. Here's our system. Okay, and if I want to ask where's the balance, you know, where do I put a fulcrum on this to, such that it's balanced? Well, okay, let me back up. How could I balance this so that it'll be in equilibrium? This is a much simpler question. Let's ask this first.
In the middle of the crossbar.
Obviously, right? Thank you. I'm going to put the fulcrum here, right? Because we have a symmetrical situation. So what does that tell me about the center of mass? Where must it lie?
On the cell line.
It's got to lie on this line. Okay, that's true, by symmetry. Okay, I'm just making it a little bit more physical here. Can it lie up here? No way. It's going to be, you know, somewhere in here, right? Right? Because it's going to be the sum of the center of mass here. Can it be way down here?
It depends on how it's weighted, doesn't it? Well, you know, M2 is.
No, this is a symmetrical situation. I think, look, forget M2 for the moment. Where's the center of mass going to lie? Right here. Now add M2. What's that going to do to the center of mass? Push it up. So we already know that it's got to lie on this axis between y is equal to 0 and y is equal to minus L over 2. So that's good. That's a check. Now exactly where it lies, we have to do a calculation. So here it is. This is actually really a definition here, but I tried to motivate it in class to explain why we define the center of mass to be this way. You sum all the moments here in the y direction. It's irrelevant what's going on in the x direction here. And divide by the total mass, and that gives you the location, the position, the y position of the center of mass. And that's what we're after here. We know the x position has to be there. So you just do what it says here. What's the total mass? It's 2m plus m2. That goes here. And then what's the moment of this? This object has its own center of mass, which is right there. Of course, it's a uniform. These are all uniform rods. But what's the distance? What's going on here? Right. I'm sorry. Let's do this one first. I'm having trouble this morning. The center of mass of this rod lies here. So what does it contribute to this sum? It has a y equals 0. Its center of mass is at y is equals 0. So this is not going to contribute to the sum of the moments here, because the distance is 0. These other ones are going to contribute equally, so I put a factor of 2 there. I take this mass and multiply by the distance to its center of mass, which is the sign distance, which is minus L over 2. And this is the no contribution from there. So you just do this and you get minus 4.4 centimeters. Now does this make sense? We should check this. Does it, we argued that it has to lie somewhere in here. Is that right? What's the length of M1? Well, the lengths are all the same. It's 22 centimeters. So you can see this is in between 0 and half of 22, which is 11. So it's in there. It's in the right range. Right? Okay. Does anybody have any questions about that one? All right, here's another one. This is not a very good diagram that I drew here. This problem is number 5, and this is an ammonia molecule, NH3. So these are hydrogen atoms here, and that's a nitrogen atom. And the way it forms is the hydrogens here form an equilateral triangle. So I went a little bit too far in the perspective. It looks, all of these, the lengths of all these are the same. So make sure you got to make sure you see that. So in other words, if we look at the top view here, where this is the x-axis, if I look down in the negative y direction, what I'm going to see here is, I just can't do it, can I? I'm going to see an equilateral triangle here. So all sides have the same length. You got to make sure you see this. See that to do the problem. So this is, yeah. So this is D. This is D, and that's D. They're all the same distance to the geometric center. This is the geometric center. Okay, everybody see that? Anybody have any questions about that? Okay, now this is interesting. We're not told the masses. Is that going to affect the center of, it seems like we can't find the center of mass. However, this thing, definitely has a center of mass, right? Oh, and by the way, what are the x and z values of the center of mass? By symmetry?
Right in the center. Right in the center of it.
So the x, 0. That's right. You're right. And the way we summarize it, the bottom line here is that the x center, the x location of the center of mass and the z location are 0. It's going to lie on the y-axis. That's the best way to say it. Okay, the center of mass has to lie on the y-axis. And it has to lie between this point and this point, obviously. So it's going to have a center of mass, right, for the actual ammonia molecule, for the actual masses here. What if I double all of the masses? What's that going to do to the location of the center of mass? It's not going to do anything, right? So all that's important is the ratio of the masses. So they've done, I think this is a good job here. You know, they're just giving us the ratio. This is all we're going to need. Somehow, in the math, it's got to all work out. Maybe some of you can see it right now. Maybe you can't. Doesn't matter. We're going to go through it right now. So here's the y location of center of mass. The sum of the moments divided by the total mass. Here's the total mass. I'm just going to leave these, you know, like they are. And the next thing to do, oh, what is the distance? Oh, I've done this sum here, right? What are the y coordinates of these masses? It's all 0, so they don't contribute to the sum. There's just one contribution to the sum for my origin here, and it's going to be the nitrogen atom, and I take its mass times this distance. And if you look at this right triangle right here, you can see that this has to be this by Pythagoras. This is going to be the square root of L squared minus D squared. Okay. That's good. Now, I'm going to try to form this. I'm given the ratios here, so I'm going to try to form it here. And you can see that we can do that. I've done. You can do it in different ways. I've divided the numerator and the denominator by the mass of a hydrogen atom. So I'm not upsetting the equality here because I'm doing the same thing to the numerator as the denominator. I'm dividing by a mass of. I can do that, right? So, and I'm motivated because this is the information we're given. So in the numerator, I'm going to get this. And what do I get in the denominator? When I divide this by the mass of the hydrogen atom, this goes and I get, the answer only depends upon the ratio, as we've physically suspected, right? So now it's just plugging in things, and you get a number. And I didn't do it here, but we could, you know, as a check, we could confirm that it lies. See, we're not given this distance, okay? But as a check, it's going to lie. It's going to lie. It's not going to lie up here, okay? We could do that. We could do that check. We wanted to. Okay. So there'll be a center of mass problem on the quiz. Oh, so I need to send out a quiz today, don't I? Yeah, I know there's too many quizzes in this class, but that's just the way. So there'll be a problem like this, an interesting practical problem. Yes, Chris?
You do have a check there because your y value up to mn is the square root of DNL squared. And since you have a ratio that's obviously larger on the bottom,
yeah,
it's going to be less.
That's right. So it's you're right. It's in the expression here. The fact that this is there's no need. It's in the expression. Yeah, good point. Okay. Any other questions or comments? So so there'll be an interesting one on the. And it's actually kind of practical. I use it all the time. Carrying something around, just carrying some object around. Often you want to support it just above the center of mass, just easier. So there's a problem like that on the quiz, kind of practical. Okay, the next one is 10. Oh, this is a good one. So you have these two skaters. There's this pole of negligible mass here that's 10 meters long. These two people are on ice. They have different masses, okay, and each starts at one end. And they're at rest. The system's at rest. And then they start to pull each other. I want to say they do it slowly, but I don't think they have to. But it doesn't really matter. So they start pulling. Each of them starts pulling. Let's see, maybe I better look at the problem here again. Hold on. So they start pulling. They're going to meet. They're going to eventually meet at a point. And the problem is, what is that point? So that may sound like a difficult. Does that sound difficult to you? Sounds kind of difficult to me. So how do we look at this problem here? Well, there's no net force on the system. This is effectively an isolated system, right? The usual thing of normal force balancing gravity. So this means, by Newton's second law for a system of particles, the net force is the total mass times the acceleration of the center of mass, right? But we've got, essentially wrote it up there. We've got zero net force. So that means that this has to be, the acceleration of the center of mass has to be zero, which means the velocity of the center of mass has to be a constant. What's the initial velocity of the center of mass? Initially, everything's at rest. So the velocity of the center of mass can't move. The center of mass can't move. And when they pull each other together like this, in the end, they're going to be right on top of each other. They have to be at the center of mass. If they weren't at the center of mass, the center of mass has to, when they're right on top of each other, the center of mass has to be where they are, obviously, neglecting the mass of the pole. So the answer, the insight that you need to do this problem is that there's going to be some center of mass here. It's going to be to the right of center because this person's heavier than that person. Okay, that's why I drew it this way. And they're going to end up at the center of mass. So we need to find the center of mass. So how do we do that? Well, we have this formula. And the formula is we have to choose a coordinate system. You can choose it anywhere. For convenience, I would choose it at one of the ends here. I'm going to do it at this end, so choosing this to be the positive direction. I'm going to choose the origin to be at the left end there, where M2 is originally located. And now the x center of mass is just the sum of the moments divided by the total mass. M1 is going to contribute its mass times 10 meters, the length of the rod, to the moment. This one doesn't contribute. So here's what we get, and as Chris pointed out, it's obvious here, this is going to be less than the length L. It's scaled by this number here, which is less than 1. So you plug the numbers in and you find 6.2 meters. Okay, yeah?
Now, why doesn't M2 contribute?
So in our formula here, there's a definition. These are the moments. It's each mass times the distance it is from the origin. The signed distance, the x location. Okay, this thing, and we're doing this initially, of course, and it won't change. So we're finding the center of mass for the masses at the end. The x value of this, the x location is 0 here. It doesn't contribute to the sum of M2.
Because we set the origin.
Because, yeah, the origin's on the left side, yeah. I know it seems strange, but it works, and it makes sense. You just got to do what it says. You got to do what this says. This is why we do problems, right? You can look at this and say, oh yeah, I understand this. And then you start to do a problem and you go, I don't understand this. So there's going to be a 0 contribution there. There's no question about it. As strange as it may seem. It doesn't contribute. It's not contributing to the moment, which is the mass times the distance from your origin. The distance is 0. So what if the pole, we assume the pole has negligible mass here. What if it doesn't? How would you solve the problem? So Well, why not just, we know the center of mass of the pole is at the center here. Can't we just, and we would be given the mass of the pole, why don't we just increase this summation, include 3 terms in the summation? And you have to put, of course, there. That's the answer. It seems like it should be a lot more difficult, but it's not to calculate it. Okay, any questions or comments about, yeah?
So the 6.2 meters, that's going from the origin?
Right, so the location of this point is from our origin, because we've chosen an origin here. That's exactly right. And it's to the right of center, which it has to be because this person's heavier. Yeah.
So the center of mass of the system doesn't change, but I mean,
In this case.
but they meet at the center of the pole, right?
I was going to ask the same question.
They meet at they're not meeting at the center of the pole. They meet here.
Well, they meet at the center of the mass of the system, which is the center of the pole.
No, I don't, this is the center of the pole. That's the center of the pole, isn't it? Right, halfway.
Yeah, but
If both skaters are pulling the
Yeah.
same distance hand over hand, and they both move their hands the same distance, the center of the pole is where they're going to meet, but the pole will have shifted
yeah,
Oh.
1
Yeah.
point,
Oh, I see what you're
or
saying.
1.2 meters to the right.
Oh, I'm sorry.
If you just stand back and look at the pole, the pole's going to shift to the
Right,
right.
okay. Good. Right. So when they're going to meet at this point.
Above the ice.
yeah.
Right. And the
Because they start out here, and eventually they're at the center of the pole.
yeah, I think you're right. I think you're right.
That's shifted over 1.2. Because, I mean, you can look at that as they're just a point mass once at the end state there, which is, I don't know.
Yeah, I think you're right. I have to think about that. Sorry, I need to think about it. So on something like this, I'll send out an email message, okay? But I think you're right. I think you're right. I just need to think about it. That's a really good point. Really good point. Thank you. Okay, any other questions or comments about this? Interesting problem, huh? More interesting than I realized. Okay, the next one is 20. So this is pool or billiards kind of question. And this is a top view. There's a cushion here. And this is the whatever they call it. This is the surface, right? And here comes a cue ball's been hit here. And it comes and bounces off the cushion, right? Now, it's apparently a good approximation. I think it's a pretty good approximation. But it is known. There's actually a book called The Physics of Pool or The Physics of Billiards. I've seen this book. So, and I've seen papers. Okay, scholarly papers on the physics of this. So it's known, and I suspect it's a pretty good approximation here that when this collision occurs here, the impulse by the cushion is perpendicular to the surface. Now there's going to be a little bit of impulse. The impulse is the force integrated over time. Okay, it's the force of the cushion on the ball integrated over time, and there is some friction here, so it's certainly reasonable to guess that there could be a horizontal impulse, but we're going to neglect that in this model here. We're going to approximate that as being zero, and it's probably a good approximation, but I don't know. So here's the information we're given. We have the mass of the billiard ball, this initial velocity, the initial speed is going to be this, and this angle of incidence here, it's called the angle of incidence, is θ1, which is 30 degrees. And we're asked we're told that the effect of the collision here is not to change the x component of the velocity. So here's this collision here. The x component stays the same, and also the y component just changes sign. So initially the y component's here, finally the y component's here, and they have the same magnitude. I represented the magnitude there. So here's a diagram of this collision here. And this side, we have a bunch of triangles here. You know, this equals this. What does it have to be true? What's the relationship of theta 2 compared to theta 1? By symmetry. By symmetry, it has to be equal. So we have a way of saying this that kind of rolls off your tongue, which makes it sound like it just has to be true. The angle of incidence equals the angle of reflection. So this is called the angle of incidence. We have this incident mass here. This is the angle of reflection, and they're equal. So this happens in optics, where it's and waves in general, not just light. Okay, so that's good. We have this relationship. What about the speed here? What's the final speed have to be compared to the initial speed? That's the magnitude of the velocity, right? Again, by symmetry, you tell me. This side, this hypotenuse of this triangle has to be equal to that with symmetry. So the final speed has to be equal to the initial speed. Excuse me. So now we can write down, and we're asked to write down what the initial momentum is in components, x and y components. So initially, we have an x component here, and you can see that it's going to be v0. We're going to write down this for the momentum. The velocity is going to be v0 times the sine of theta 1 in the x direction, because the hypotenuse times the sine of the angle gives me this. And I'm going to multiply by the cosine to get the y component. And then I multiply overall by the mass to get the momentum. So this is the initial momentum. This is the momentum in the x direction, which is the mass times the velocity in the x direction, which is this or that, same thing. And this is the momentum in the y direction, which is the mass times the velocity in the y direction. Up here. So it involves a cosine. So that's the initial momentum. What's the final momentum? Well, the final momentum, the y value has been flipped, and momentum's conserved in the x direction here. We're neglecting that frictional force. So we're assuming there's just a normal force here that does this, is responsible for this impulse. So momentum's conserved in the x direction here. That's the best way of thinking about this. So in the x direction, you'll see we've got the same final and initial. And in the y direction, it's been flipped. So you can see that here. So the change in momentum, which is the final minus the initial, is just going to be in the y direction, and it'll be given by this. And we have a negative sign here because it's started off in the plus y direction and ended in the negative y direction. So it's going to be negative. And the momentum has units, SI units of kilograms meters per second. And this has to be equal to the impulse supplied by the wall. The integral of the force over time, which is probably very complicated in a collision here, has to be equal to this. It's really by definition, that's how we define the impulse. Okay, any question about that one? Comments? We've thought about purchasing a small billiard table for physics demonstrations, right? I keep thinking about the part, what?
You get full size.
Right. Yeah, right.
And then we'll set up a room right back here. It'll be fine.
Some of the
Okay, I probably could justify that. Okay, I've done worse than that.
We have a
But wait a minute, where are we gonna store it? You see, you guys aren't thinking. You just want to play some pool. You know? We need we need an addition to the demo lab.
Or you can just put it in the middle of the hallway.
My living room works too.
Right. So Yeah, I think because there's a lot. We've already been talking about it, right? English, spin, that's just the beginning here. There's a lot of physics in there. And like I said, there's an entire book on this subject. You can Google it. I'll bet it's in there. I think it's called The Physics of Pool or The Physics of Billiards. You're going to find it, I think. I may even have a copy in my office. I can't remember. It's not a huge book, okay, but it's a book. Okay. So one of the classic problems is this, and we can almost do that. We could do this at this level, but it's a little too complicated. Okay, so it's normally done at the next mechanics course. The situation is, this is the cushion, right? Looks something like this. Here comes this ball, right? How high should the cushion be? And you might think, well, it doesn't, I don't know, halfway, or it doesn't matter as long as you don't want it to get close to the diameter here, and you don't want to get it way down here because the ball could go over. So how high do you make this thing in relation to the radius of the ball here? So you might think you have a range. Pardon me?
3 times.
I couldn't hear.
Just slightly taller than the radius.
Yeah, that sounds reasonable. It's not right. Anybody know the answer? I used to know the answer.
Isn't it as high as the center of mass is on the ball?
Well, that would be.
That would be R.
Yeah, no, you're not going to get the right answer.
You have to purchase the book.
Yeah, by the way, I'm the author of the book. So the answer is something like 5/7 of the diameter here. How'd they come up with that? Well, when the ball, it's desirable here, when the ball comes in, it's rolling, right? Typical case when it's rolling. And we should actually save talking about this until we get into rotational dynamics, but I'd probably forget then. When the ball comes in here, if the cushion is halfway up and you reflect the ball, it's still going to have this spin. So what's going to happen when the ball comes in here and it reflects back? It's going to skid. It's going to skid. So you want to hit it here. Want to hit it at a certain height here, such that when it comes in like this, you reverse the impulse here reverses the spin, and you can calculate that. But I don't think we're going to do it in this class. So this is an example of why there's a lot of physics here. Get the idea? What I just said about that? Yeah. If you do it halfway, it's rolling in. There's going to be very little impulse this way. The main impulse is this way, so you're not going to change that rolling. So just after the collision, it's still going to be spinning like this, so that it introduces friction. You're going to lose mechanical energy. Interesting, huh? Yeah, we need to buy a small, full size. I can't believe. Okay, so is this the next one? 26? Is that right?
Yeah.
So this is real. Somebody in 1955, somebody was parachuting, their chute didn't open. They fell 370 meters and the chute didn't open. And the person walked away from the, you know, it's a good parachuting accident when you walk away from it, I guess. Walked away. This has got to be real, right? So what happened was a person landed in snow, and that broke the fall. Broke the fall. What does it mean, break the fall? Well, yeah, it's specifically, what?
Inelastic.
Yeah, it's going to be a pretty much nearly perfectly inelastic collision, whether you hit snow or concrete, right? You'll probably bounce a little bit from the concrete. I don't think it's going to matter to you at that point, but remember the boxing thing, the padded dashboard thing? You want to spread that collision out in distance or time, right? So that's what happens. So in this, evidently data has shown that a person can handle a certain maximum force without being, permanently injured or something like that. So we're given what that is here. It's 120,000 newtons. We're going to assume, because this person survived, that was the force of the snow. Now the actual force could have been less than that, but we're going to find the minimum distance to bring this person to rest without hurting the person. So we're going to take the maximum force, that's survivable force. We're going to assume that's the force of the snow. Again, the actual force could have been greater. That's okay, that's good. That's going to be better. So during the collision here, this is huge. We can neglect that. That's actually the impulse approximation. We don't need to worry about this because this is so huge during the collision. And we're just interested in during the collision here. The person hits with some initial velocity, which is the typical of the terminal velocity of the person here. Now, the terminal velocity is going to depend upon the orientation of the person, right? And the person's wearing this, it's going to, but this is a rough value for the terminal velocity. So let's just use simple Newtonian mechanics here. We have a constant force, we have constant acceleration. We use the no time, we don't care about time. This is the no time equation. You'll recognize it. The final velocity is 0. We know the initial velocity. What's the acceleration? Well, I should have written it here, but this force here, the net force is of course the mass times the acceleration. So, please ignore this. In going from here to here, I multiplied numerator and denominator by m. But I think it's better in this class to just say, we need to get rid of this a, and I know that it's the force divided by the mass. So that's what I've substituted in going in the next step. So please just forget this step right here. Right. So, I got a little ahead of the story here. We can solve. We have one unknown here. It's y. That's the distance over which this acceleration or deceleration, whatever you want to call it, occurs. And we can calculate. We can solve for y and plug the numbers in, and we get about a little over a meter, which seems. I wouldn't want to do this experiment with my body, okay? Because that seems kind of short to me. But that's what the numbers show here. It's surprisingly short. I would have guessed, like a factor of 10 or 5 meters. Okay, maybe 3 or 4, but this just seems short to me, yeah?
So when you say 1 meter in the snow, that means he fell 1 meter, the snow is at least a meter high?
That's the minimum distance he would have fallen in this once he makes contact with the snow. This is the velocity right when we're looking over the motion we're looking at is just before just as the contact is made with the snow, and then the person comes to rest. That's the minimum distance for the person to survive, approximately. You wouldn't want to bet your life on this, right? There's a lot of approximations here. Yes?
So, something I did with this problem, you're able to figure out the acceleration. You just take, if you know the force, and you know the final velocity is going to be 0, so your change is going to be 56, or at least the force divided by the mass. It's going to be a really quick acceleration just hitting snow.
Yeah, we can. The acceleration, I've actually calculated that here. The g-force is amazing. So that's often how people will compare. I think we've talked about this before. That's often how they compare an acceleration, especially when somebody's subjected to this. It's 144 g's, which we've talked about this before. Somebody said 10 g's is unbearable, but that's constant. This is over a very brief time interval. So I've added that in my notes. Yeah, this is misleading, okay? It's not just the g-force that's important here. It's the time over which that acts. And that's the collision time, which is going to be pretty small here. And we could calculate it. Maybe that's what you were talking about. You can calculate the collision time. The time it takes to, yeah. What do you get?
I just knew that. I didn't actually do that, but I got the same 1.1 meters when I just did the acceleration, not having to substitute force and mass.
Yeah, there's going to be different ways of doing this, right? So I've done it, you know, algebraically here, and then waited till the end to substitute the. Usually you do that because you can. Sometimes there's simplifications, and we've talked about that before.
The other thing is, there's a big assumption of the terminal velocity. I'm not, so my first question for the reality of this is, well, how did they arrive at that? Because,
They don't tell us.
Right, just because the chute didn't open didn't mean that it wasn't slowing him down a little.
Right. And, the person, if you imagine yourself going through this, it's not going to take you long to realize that you're just going to go spread eagle, right? Now, there's a problem with that. That's going to tend to be unstable. Remember? This is unstable, right? See it start to go like that? It's a little too heavy. We did this along, yeah. So there's a lot of problems here, but you're going to try to present as big a drag get as big as drag force as you can, right?
Yeah, 0.04 seconds to go from.
Yeah, so we would call that 40 milliseconds. We would go to milliseconds, right? Which is, it's roughly typical collisions are like that. I don't know if this is a typical collision or not, but that's, yeah. So evidently you can handle a huge g-force, but as long as the time is brief, sufficiently brief. Okay, next one is 44. So here's an explosion problem. Here's the initial state, and this mass explodes into two fragments. Okay, it's moving in the laboratory, in our frame of reference here, the laboratory frame, whatever you want to call it, and it explodes, and it's a one-dimensional collision. Okay, I mean, in general, when this collision occurs, this could be going that way, and that could be going that way. We're just focused on a one-dimensional problem, and we're restricted to that in this class. We just don't have time to get into unfortunately, to get into two-dimensional collisions. And so we're asked for how much kinetic energy is added to this. So this explosion is going to add kinetic energy to the system, right? And that's what we're going to go after here. Now, this is an isolated system, so momentum has to be conserved. The initial momentum has to equal the final momentum. Now we've got a problem here, a little bit of a problem. What are these masses right here? Well, if we neglect the mass of the explosive, then these have to sum to be this initial mass here. All right. So we're imagining, there's this massless compressed spring that we start off with these two masses, and there's a compressed massless spring, right? And then our explosion is this. You can imagine it that way. This spring goes to its equilibrium length, releases that energy. So m prime has to be a quarter of m here, because this mass is going to be this mass, neglecting the mass of the explosive. So now we can write down momentum conservation. The initial momentum is m times v0. The final momentum, we're told that this one is at rest. So the final momentum is just going to be the mass, which is 3m prime, which is equal to this. This mass right here, 3m prime, is equal to this from here, times the final velocity. So we can solve for the final velocity in terms of the initial velocity. Now we're not given numbers here on that, but that's okay. We now have the final velocity in terms of the initial velocity. The initial kinetic energy is 1/2 mv0 squared. The final kinetic energy, it's all in this mass. It's 1/2 times the mass, which is this, times the square of the velocity. And we substitute this expression right here into here. We don't, it's okay. We don't have definite numbers here, but we can just do this algebraically. And then we simplify. We substitute this expression into here, simplify. We did a similar thing in class, in lecture. And we get 2/3 mv0 squared. So look at that. This is interesting. Has the kinetic energy gone up or down or remained the same? It's gone up, right? And that's due to the explosion, or the spring, if you like. If you want to think of it from a conservative force point of view, put a spring in there, have a compressed spring. So that energy has come from the explosion, or from the spring. Okay, any questions about that one? Okay, so here's another collision problem. This is this is 55, and it's like, this is like a toy cannon. If you look at the numbers here, these are small masses. So the physics of the situation is that we have this projectile, a mass coming in, and it hits this mass and spring system here. And at the moment of maximum compression, when the velocity of these two things is the same, you put a massless clamp. You imagine, this is a Gedanken experiment, we talked about that, I think. You imagine putting this massless bracket on here. All right? Now, at the moment of maximum compression of the spring, the system's not moving, right? The masses are at rest, right? Is that right? What do you think? No, it's not right. When this mass comes in and starts to push on the spring, it's going to push this one. It's going to cause this one to move. So the collision here takes place over some distance here. It takes place over some time and some distance. These will have moved to the left. But finally, at the maximum compression, this clamp or bracket is put on here, and then we have just one object. So this is a perfectly inelastic collision. The initial momentum's given by this. The final momentum, this is really easy, right? Oh, I'm choosing this as my positive direction for convenience here. Let's choose going to the left as positive. This is an isolated system, so the momentum has to be conserved. So that allows me to determine the final momentum. And now I'm going to plug the numbers in. We came up with the same expression in lecture yesterday. Plug the numbers in and we get a value. That's the final speed of this single mass here. It's effectively a single mass. There's going to be some changing kinetic energy. You know there is. Where does the kinetic energy go in our physics system here? Into this exactly the same amount. The mechanical energy will be conserved here. There's no friction, no non-conservative forces. So there has to be a decrease in kinetic energy, and we can calculate it. Here's the final kinetic energy. Here's the initial. Plug the numbers in, and we get that the kinetic energy goes down by this amount. By mechanical energy conservation, the identical amount of energy has to be stored in the spring. The fraction of the stored energy, which you're also asked for here, is the stored energy, the energy in the spring, divided by the initial energy. Okay. Divided by the initial energy. And it's 80%. Wow, that's big. Why is it big? Why is it big here? Let me tell you, it can be anything between 0 and 100. But why is it big here? What's causing that? What if this were a very big mass? What would happen? What if this is very large compared to this? And incidentally, it is pretty large, factor of 4. But go to the extreme case, when this is much bigger than that. What's going to happen? Is it going to move?
No.
So what's going to be, in that limit, what's going to be the fraction of stored energy? 100%. Right. So we're getting this high value here because this is substantial. It's a factor of 4 greater than that. Yes. And it would be the opposite if it were lighter. Yeah?
I'm just not sure why not knowing the spring constant isn't a factor here.
Because if you imagine putting a weaker spring in here, what's going to be the difference with a weaker spring?
You would have non-conservative losses.
No, this is conservative. The collision will take longer, right? The spring's weaker, but the stored energy is going to be the same. And this is an excellent question. In a perfectly inelastic collision, it just doesn't matter. You got to bring those masses to rest. How you do it really doesn't matter. Momentum conservation doesn't care. Here it is. Our information is falling from momentum conservation. It doesn't matter what the interaction is. So if you could have a piece of clay there and hit and somehow stick, you can have different springs. You're going to lose, the same amount of energy is going to go in. It's going to go into the internal energy, whether it's friction or a spring. Right, it's a good question. I know it doesn't seem right, but
Is that gonna help?
look, there's an impulse. Think of this in terms of impulse. This thing's coming along here, and it's exerting an impulse on this, causing to change its momentum. But this is exerting an impulse on that, and they're always equal and opposite. So in the end, you start off like this, and in the end they're moving together. They've each exerted impulses on them, on each other, such that they come to such that they have no relative velocity. They're moving together, and it really doesn't matter what the nature, what the details there. It's not going to matter whether it takes place over a long time or a short time. I don't know if that really explains it. Maybe that doesn't help. I thought it would help. Yeah, it doesn't matter here. Because we've got to go from this state where these two things, where this one's at rest, and then finally, this one's at rest, and finally they're together. And the initial momentum has to equal the final momentum. And that tells you right there that it doesn't depend upon the details. And this is often the case in collisions. The details don't matter about the nature of the interaction. Okay. The next one, which fortunately is the last one, here's the system. This is a frictionless track up to this point. And in part A, so we release this from rest. It's going to come down here, and it's going to have some initial velocity, which we can calculate by energy conservation. All right, this is a curved track. You wouldn't want to use Newton's second law here and integrate it. We just want, this is a simple problem in energy conservation, as we discussed last chapter. So I can find the initial velocity with which M1 is going to hit M2. And by the way, M2 is twice M1. So we're going to look at two cases here, elastic and completely inelastic. So what if the collision is elastic? What's M1 going to do? Is it going to be momentarily at rest after the, is it going to come to rest after the collision? Is it going to bounce back, or is it going to follow the mass?
It's going to follow what you said in the last one.
It's going to bounce back because this mass is greater than that mass. When the masses are equal, this will come in, it'll go like that. When this mass is greater, it will follow. And we have a formula to tell us what's going to happen there. We have actually two formulas, one for the final velocity here, just after the collision, and one for the final velocity here, just after the collision. We're going to use that formula. You can look it up. We didn't derive it. We didn't have time to derive it, but it's in the notes and in the book. So here's the velocity of V2 after the collision. We can calculate that because we know V0 is the square root of 2gh. So we plug numbers in, and I get to three figures, I get 4.67 meters per second. Now we can find, and we did this long ago in friction, we can now find how far this is going to go. If you tell me the coefficient of friction and an initial velocity of a block, I can tell you how far it's going to go, right? That was one of the first problems we did. So we use the no time equation here, and we get a distance. Now let's ask, what's the distance if these two masses stick together? So that's a completely inelastic collision. Well, now we can easily find the final velocity. Here it is. See the momentum, don't look at this. See the momentum conservation there? Final momentum equals initial momentum. So that allows us to find the final velocity. And when you compare the expression here, here's why it's nice in this case to do this algebraically, to hold off plugging the numbers in. You can see that I get 1/2 this completely inelastic collision. The block here, the combined block, is going to have 1/2 the velocity for the elastic collision. So it's how far is it going to go? Well, the distance traveled from up here, from right here, which comes from the no time equation, you'll notice that the distance it's traveled is given by this expression. So if we have the velocity, it's going to quarter the total distance traveled. So it's not traveling far because it's a heavy, we have less velocity. Because of that perfectly inelastic collision, this thing's moving less fast. But you might say, well, wait a minute, it's heavier. So isn't it going to go farther? Nope. How does the distance depend upon the mass? Where's the mass in there? It's not there. Can you see it's not there? The reason it's not there is, the heavier it is, if I double the mass, I double the frictional force, but I've doubled the inertia. That makes it harder to come to rest. The two exactly cancel. They exactly cancel here. And I can't remember if we pointed this out or not when we were doing friction. Okay. That's it.